Okay, so welcome back to lecture once again, guys. Now, in this lecture, I'll be talking about a word to vector. Now, word to vector is another method, another technique by which you can convert your entire data into a vector representation, or you can say into a numerical representation. You will be able to convert your data. The best part about word to vector is that whenever you are going to convert a data with the help of word to vector, it is going to consider even a semantic meaning of the data, and then it is going to convert, not like a bag of word or TF-IDF, so where it was trying to consider just a frequency or occurrences, number of occurrences of the data set. So now let me share my screen and let's start talking about it in a practical manner. So word to vector is a model, I can say. So like a deep learning model, a neural network model, which people have already created it, and I'm just going to import it. Import it from where? From a gensim. So by default, gensim will not be available. So just try to do a pip install gensim gensim. In my system, it's already installed, so you all will be able to install it. Yeah. So pip install gensim, and it will be able to install it in no time. As simple as that. Now here, so if it is going to give you a problem with respect to NLTK, so just try to do that once again, and it will be able to install NLTK as well. Now here is a sentence. So I love deep learning. Deep learning is a part of AI. Word embedding captures meaning, and I love NLP. So this is a sentence which I have taken. My primary objective is to convert this entire data into a vector representation. Yeah, into a numerical representation. So how I can do that? So let's call the sorts, and then let's start doing it. So for I in sentences. Yeah. So for I in basically sentences. Why it is not giving me the auto completion? Okay, let me restart. Okay, so import and then I in sentences. Okay, so what we are going to do is that we are going to convert the entire data into a lowercase, plus we are going to tokenize it. Tokenize it means we are going to break down the entire data so that I will be able to pass the data inside my word to vector neural network. Yeah, so word underscore tokenize, I can try to import. So here word tokenize, I can try to import. Tokenize, I can try to import, and then whatever data that we have, right? Whatever data that we have inside it, so we can try to convert that data to the lowercase, right? We are trying to normalize the data. Now, so we are going to store this data into tokenize sentence. Yeah, so inside this we are going to store it. How my data will look like? So I believe we all know how my data will be look like. So here a word tokenize, and this is how my data set will look like. So here word tokenize, I can try to show you my data. Tokenize, and then yeah, so this is how my data set will look like. Yeah, so I love deep learning. As you can see, there is a list, and I love deep learning. So all these things is been tokened, means in a single word it has been converted. Now again, so deep learning is a part of AI. So again, in a single word it has been converted. Word embedding captures capture meaning. So again, in a single word it has been converted. Again, into the single word it has been converted. Simple, right? Okay, so this is called as tokenization. So we are able to tokenize our data. Now, so after tokenizing our data, so we can try to call a word to vec, a neural network, which we are trying to do an import from a gensim library, and then we can try to pass our data. So we can try to pass this tokenized data, because that will be the expectation. So here word tokenize, we can try to pass as a parameter, right? As a parameter we are going to pass. So sentence, I can give sentence is equals to word tokenize that we have done. Now I can say that vector size is equals to 100. So vector size is equal to 100 means, so here we can try to control that what should be the number of the feature or number of the column. So in case of TF-IDF, in case of bag of word, it was trying to take a number of unique word, right? It was trying to take the unique word. So we can try to control that over here. And there is something called as a window. I'll try to give you the explanation about it. So let's suppose we are keeping window is equal to 2, and then minimum count is another parameter. So let's suppose I'm keeping at 1, and then there is a parameter called as SG, which full form is a skip gram. So skip gram is equals to 0. I'm going to give. Now, what is the meaning of this window is equal to 2? Meaning count is equal to like 1, and SG is equal to 2. Let me explain that part in a first. Okay, so what is the meaning of, by the way, a window over here? So when I say window is equals to 2, right? So when I'm trying to say window is equal to 2, it simply means that it looks 2 word before and 2 word after, right? So in terms of building a context of the entire information. So vector size is 100 means, so your entire dimension of this data which it is going to build, or numeric it is going to build for each and every sentence, is going to be 100. So if you have like a very high vector size, in that case again it will be problematic, because it is going to consume more and more memory. If it is very low, so maybe it will not be able to capture the context of the data. So here we are keeping window is equal to 2. Window is equal to 2 simply means that it looks at 2 words before and 2 words after the current word for building a context, as simple as that. Now here, so minimum count is equals to 1. So what I'm trying to say, that if there is some data which is not having a minimum count is this much, remove it. So let's suppose if I'm keeping minimum count is equal to 2, and if we have some sort of a token, so which is not appearing 2 times in my whole data, it will remove automatically. So as of now, I'm keeping minimum count is equal to 1. So even if data is appearing only 1 time, it will keep it. It will retain it. Yeah, it will retain it. So this is the, so basically it ignores all the word with the total frequency lower than this much. And then we are trying to give SG is equals to 0. So basically when we are trying to call this word to vector, so it try to follow 2 things. One thing is basically CBOW, CBOW, continuous bag of word, and there is something called as skip gram. Skip gram. Now what is the difference between continuous bag of word and the skip gram? So continuous bag of word, right? If I'll talk about this one, so it will always try to predict a word from the context. Yeah. So it will always try to predict the next word from the context that you are going to give. And when I'm talking about a skip gram, so a skip gram will always try to draw, or always try to basically predict the context out of the word. Very simple, right? So so skip gram, let's suppose if I'm going to give love, so it is going to maybe predict the context. I love deep learning, right? And here, so if I'm going to give I love, so it will predict the next thing. So this is what a difference between CBOW and the skip gram you will be able to find out. Now let's move ahead, and let's skip gram is equal to 0 means I'm talking about a CBOW, by the way. So this is what it means. So here I can try to maybe store it as a model underscore CBOW bow. So continuous bag of words. So where I'm going to give a context, it should predict a next word. In a skip gram, it's a reverse of it. So I can try to keep all the things as same. So I can just try to change skip gram is equal to 1. So skip gram will be activated, and model is equals to skip gram. Yeah. So this is one model. This is one model that we are going to build. And here, so we are going to pass, let's suppose, some sort of a data. So model CBOW, we are going to pass basically a word vector, and we are going to pass basically LOVE, love. Now, so it is going to give me some sort of a output. Dimension of this output is, so dimension of this output is going to be 100. Now, so if we are going to give model dot word vector dot most similar, so here if I'm going to give love, so again it is going to give me some sort of output. So here, as you can see, so we are trying to give a love, and then we are trying to see that which word is most similar, or I can say like a nearby to this word called as love. So the nearest one is basically a word, then the second nearest one is part, and then an NLP, then capture, then meaning is, and so on, right? So this is something that we are able to predict from this skip gram. Now, whereas from this small.cwow. So we are trying to get a vector for this particular word. So we are going to get basically like a information out of this entire data. Let me show you. So what this data is technically representing. So again, same thing I'll do over here. So what I have done are more similar, right? So here I can try to call wv word vector dot most similar, right? And then if I'm going to execute it, oh my bad, so I should pass that as a functional input. Okay, so here again you will be able to find out that in case of like a most similar for a love, if I'm using a CBOW is these data, and if I'm using a skipgram, again these data. Maybe it's a similar, right? It's a similar to each other. That's completely fine. But at the end of the day, right? At the end of the day, so we are trying to find out a most similar. Not just that. So we are trying to find out even a representation of a one single word. So for example, what is the representation of the word love? So this is the representation of the word love. Now, so if I'm going to like give maybe, if I'm going to give maybe my name Sudhanshu over here, will it be able to give me a representation? Obviously no. So because Sudhanshu is not available, Sudhanshu is not present in my original data set. So here you can try to pass any of this data which was already available, inside my data set, and for those data only it will be able to give you a vector representation. For example, if I'm going to pass embeddings and embedding was available, so it is trying to give me a vector representation that, okay, so in a numerical space, this is how embedding looks like. So when you are trying to use a word to vector CBOW, as simple as that. Yeah, so as simple as that. So it is basically trying to like represent that how love is been used in the context, means how we can try to use love, or how we can try to use this embedding in this particular context, as simple as that. Yeah, so this is a 100 dimension representation of our embeddings. Similarly, so I can try to maybe like find out and embeddings for all the other data as well. For example, a learning. So I can try to pass a learning, and it is going to show me that how learning actually looks like in a 100 dimension. Simple, right? Now I can try to control it. So let's suppose I don't want to represent this entire things in a 100 dimension. So maybe I would like to like represent this with 10 dimension only, not an issue. So here, just with the help of 10 dimension, it is trying to represent the same data. So I can control it. Yeah, I can try to control it as much as I want. Very simple, right? Okay, so with that, thank you so much everyone. Take care, and see you again in my next upcoming lecture.